Our next speaker is Kyla Guru. She's a graduate student studying computer science and international relations at Stanford. She's also the founder and CEO of Bits and Bytes, a cybersecurity education. And her talk today is end-to-end framework using LLMs for technique identification and threat actor attribution. Please welcome her. Thanks.
Yay. Okay, I always got to bring my water up here because I'm suddenly find myself choking on words. But hi, everyone. I'm super excited to be here. My name is Kyla, as was mentioned, and I'm a master's student at Stanford University. I work at the Stanford Intelligent Systems Laboratory, and my research focuses primarily on the use of large language models for cyber threat intelligence tasks. And my research today is going to talk about the exploration of an end-to-end pipeline for threat actor attribution using LLMs. So before we jump into it, I want to transport you back to 2021 to a cyber attack that most of you probably remember pretty closely. So when we think back to the Microsoft Exchange Server campaigns of early 2021, we saw that NATO and EU member states failed to achieve consensus on an attribution and denounced China's use of contract hackers. And this was said to have happened in large part because of failure between member states to join in on an attribution answer. And I know there's different definitions of attribution in the AI community and in the cyber community. Today in my presentation, we're talking about the cyber community's definition of attribution. So this is attribution of a threat actor post-attack. So given that attribution is typically achieved through independent verification between countries, inequities compound into delays on a global scale. So correct and timely attribution helps eventually shorten future response times of cyber defense teams and informs mitigation strategies and helps for a nation's self-defense. So let's dive quickly into what attribution looks like today so you can sort of see why this process takes so darn long and see why we could maybe use some additional technologies to help speed this up. So when a data breach occurs, digital forensics is conducted on affected systems or a network. From the forensics, a case file is constructed, and this has all the details of the attack, what occurred on the network and the computer in, during, around, or after the attack. After this is when a human analyst comes into the picture and based on the case file, tries to pick apart the dense forensic technical details and build what we call a diamond model, find exactly what was the behavioral MO of the threat actor and what their tactics, techniques, and procedures, or TTPs, were. So these TTPs are typically standardized to the MITRE attack framework, which I know a couple of you were just at the attack conference before CAMLIS. So given this information so far, yay, attribution is conducted on the information provided by the analyst. But not yay, this process typically takes months, if not years, to actually gain technical attribution. So while the current literature demonstrated a lot of ways that machine learning has been applied to this space before, one space that has not been applied that much is LLMs. So additionally, the research that's been demonstrated has not been end-to-end approaches. So it hasn't been putting in a document and getting out actionable intelligence from that document. So since attribution has so many language-centric tasks, this is what I wondered, I wondered whether the technology of LLMs has a place for analysts who do attribution. And since there weren't any basic studies looking at the performance of models that haven't been fine-tuned, I wondered what the raw capabilities of the models were to do tasks like this. So diving into my research question asks, how do LLM-enabled pipelines impact the efficiency and accuracy of attribution? To study this specifically, I split this up further into two questions. The first being, how do LLMs impact the identification of tactics, techniques, and procedures from dense forensic information? And secondly, how do these extracted TTPs eventually, how can they be used to train a more classical machine learning model to attribute a threat actor post-attack? So first I'll talk about my methodology and results from the first research question, and then I'll move on to the second and tie it all back together, hopefully, at the end. So to answer the first question of TTP identification, I focused on two core methodological approaches. And I compared the output of these approaches to human-generated output used from MITRE. So I will say a limitation of my study is that the approach is that the MITRE TTPs are open source TTPs that researchers have added almost like a Wikipedia onto the MITRE webpage. So it's not the greatest and fullest representation of the full nuances of a threat actor's TTP actor set. So the first approach that I had to TTP identification looked at a raw pipeline. So can we just take a raw PDF of cyber threat intelligence from the MITRE website, prompt engineer GPT-4, and provide me a list of TTPs that represent the document? From here, for each threat actor, I collected a TTP set that represented their activity altogether and then compared this with human-generated TTPs. I automated this collection for about 29 threat actors and had all these threat actors had 10 or more references associated with them on MITRE, and I collected all of their generated TTPs and human-generated TTPs. Similar to this, I looked at another approach to do TTP identification. I also compared a vector embedding search approach to the raw GPT approach. So the way this worked is that my approach looked at a document by splitting it up into chunks. For each set of 3 lines, I crunched a vector embedding that represents this line of set or words. From here, I compared that paragraph's vector embeddings to the vector embedding of all the TTPs in the MITRE database. And I took the TTPs that had the highest cosine similarity or the closest semantic similarity to the paragraph's embedding. So this, whatever was resulted from the vector embedding approach, was also compared to the human-generated TTPs. Cool. So what I found was that in both cases of using both GPT-4 and vector embedding search across these 29 and 30 threat actors, the model had high variation to human-generated. Oops, I went back. Forwards we go. The model had high variation to human-generated TTP sets. So at the same time, there were specific strengths and weaknesses of both approaches, the GPT-4 approach and the vector embedding approach that I wanted to talk about. So specifically, the GPT-4 approach had the benefit of having prior context about TTPs or about the incident, and also being an off-the-shelf solution. At the same time, GPT-4 was more of a black box. It would produce TTPs that sometimes had different sub-techniques that didn't even exist within MITRE. You wouldn't have a correct sense of how it came to its answer. On the other hand, the vector embeddings approach represented a way towards increased interpretability. So instead of just on the MITRE site, how you see Lazarus Group having XYZ MITRE attack techniques, this approach rather represents a probabilistic approach. So this says that, oh, Lazarus Group uses this TTP 3 times more than this TTP, or has specific fractional percentages with that. So an analyst can go in and see relative rankings of each TTP assigned to a group and see the probability distribution across all TTPs for one group. This is a huge step up from the binary yes or no that you see on the MITRE website or on the internet in general. So since the analyst is in control of the TTPs they're reading from, there's also no risk of hallucination. And the limitations of the vector embeddings approach is that there's a lot of parameters that you need to sort of fine tune, not as much as like hyperparameters, but these parameters are like, do you want to do a sliding window approach or a set window approach? How many lines determine a chunk in a paragraph? Is it 3 lines, 4 lines, 5 lines? So there's a lot of kind of fine-tuning that goes on there to figure out what results in a high similarity or any similarity in general. So interestingly, I did see an interesting trend among the frequency of TTPs outputted by GPT-4 and those on the MITRE website. There's a strong positive correlation on this graph, meaning that if a TTP was more popular within the MITRE set, it was also likely popular within GPT-4's output. This could have been because GPT-4 was trained on the MITRE dataset. It also could indicate that if you do extra fine-tuning and training on the proper context, we might actually have a high similarity to those in the human-generated dataset. So another interesting observation here is that GPT-4 and MITRE actually tended to err on the side of providing more general MITRE recommendations for the techniques. So they would look through a paragraph and say, spear phishing, or scripting techniques, because those were fairly common and used across threat actors. So it would make it really hard to use that for any sort of technical attribution, because they're such common indicators. Cool. So next I looked at the full end-to-end pipeline. So how could we potentially use these TTPs for attribution of the threat actor? I also tested 2 different approaches here, and I'll begin by talking about the vector embeddings approach. So for the actual attribution, I developed a machine learning proof of concept using over 720 documents and generating an ordered list of attribution given unseen documentation. So what the model does is that it crunches vector embeddings and generates weights for each MITRE code per threat actor. From the training phase, we then have a weights matrix. So when you're given a new unattributed document that says input, the model uses the generated weights to make a prediction. The prediction is represented by this ordered list of threat actors on the screen. So each strength of the threat actor is also added on the screen there. So the eventual output of this model is that you're able to input a document that it hasn't seen before that hasn't been attributed, and it will output a list of threat actors that it potentially thinks is behind it using the TTP pipeline. So first, I'll talk about model performance a little bit. So the baseline model performance for a task like this is just random guessing. So the baseline of 15 is sort of what I used for looking at the 29 threat actors that were in the data set. And the average correct ranking after the training process was about 10. So this is correct ranking is like where in the ranking out of all 29 threat actors is that correct threat actor. And then once we included expert feedback, which I included as a threat actor relevance component, so how relevant was this threat actor at the time of the attack in general, the performance improved even greater to an average ranking of 7.5. So we also used an emerging approach called HIDE to help strengthen some of those TTP definitions and the embeddings of each TTP definition. So through fine-tuning parameters and including the threat actor relevance factor through expert input, the performance of the model increased. And so this still is low. It could use a lot of fine-tuning, but the model's baseline performance was 15. So that improvement shows us that the model is learning underlying patterns using solely behavioral information from the attack. And as many people in threat intelligence know, behavioral information of the threat actor is just one piece of this puzzle. There's also victimology reports. There's information about the infrastructure of the threat actor. So I think a next step of this research would really be cool to see how all parts of the diamond model could come together to create a stronger attribution. So another cool part of the research is that I found that the end-to-end pipeline also performed better on some threat actors than on others. So for example, there were 2 threat groups that stood out and they performed poorly, even though there was a large amount of data about them within the data set. So when taking a closer look, Lazarus group and menu pass both appeared to have high entropy and high cosine similarity. The high cosine similarity represents that the similarity of this group's threat actors to another group's TTPs in the whole set. So similarly, high entropy is the high randomness among the TTPs. So basically, it means that these 2 groups were doing everything across the board. They're kind of random actors. And in threat intelligence, we know Lazarus group actually has a lot of different clusters. So their variety of behavior actually quite makes sense in this case. So in general, the analysis finds that Lazarus group and menu pass are outliers in this data set. Even with a lot of training data on these threat actors, the outputs will have high cosine similarity and high entropy. So these threat actors likely don't have a clear technical signature that we can determine even using a lot of data. So without these 2 threat actors who are outliers, the graph demonstrates a negative correlation, demonstrating that when you have more data and when we create the vector embeddings using more data about the threat actor, it actually results in better downstream attribution. So kind of following suit with a lot of the scaling laws in LLMs right now, which is pretty interesting because I think in my research, there were groups that didn't have as much data about them. If y'all have heard of the notorious and mysterious equation group, that's a US-based group, groups like that, they would perform significantly worse in attribution because there's less data. So that just shows that with more data and more people doing open source research and open source threat intelligence sharing, it's only going to bolster some of these results. So basically, I wanted to talk a little bit about what I did for kicks and giggles. So for kicks and giggles, I wanted to experiment with what happens with human in the loop on GPT-4's raw attribution capabilities. So I looked at a May 2023 attack by Kim Soo-ki, a North Korean threat actor, to conduct this experiment. So I first extracted the TTPs from a redacted form of the report in one window and tested the ability of the model to generate attribution results in another window. At first, GPT-4 was producing threat actors that were very, very common. So APT-29, 28, Fancy Bear, it was just guessing the most notorious threat actor in the playbook. In the next round, I added screenshots of specific scripts used by the threat actor in the terminal window. In the next round, the answers became slightly more specific. The threat actors were still incorrect and vague in general, but the answers became slightly more specific. And then lastly, when I suggested the specifics around the malware sample that was used in the attack as a variant of Baby Shark, the well-known North Korean malware, GPT-4 immediately changed its point of view and provided the correct attribution. So again, human in the loop, this continuous cycle of improving the model's knowledge and context of the attack highly improves the results. And I think that's a pattern amongst what you've heard with speakers today, is this human in the loop component. So as a summary, I presented two approaches in this research. The first question was to answer, how do LLMs work on just TTP identification? The second was to build this entire pipeline from TTP identification all the way to attribution. So to answer that first question, I'll bring these up. So different TTPs are produced by LLMs than humans, no surprise there, but it was something that was pretty determinate and big in my results. But the TTP frequencies do match MITRE, which is quite interesting. And then to answer the second part, we see that even though the TTPs were different than human extracted TTPs, that didn't make them any less useful for attribution. They still did improve model performance. Training a model on these results still leads to some sort of difference in terms of improvement in attribution results. The solutions work better on certain threat actors over others, so seeing these kinds of approaches can actually help us determine which threat actors machine learning models will work better on versus worse on based on their techniques, and could even help determine which threat actors have more of a rogue pattern of doing every single threat actor technique in the playbook versus which ones have a very unique signature to them. And lastly, contextual information from human analysts definitely improves performance. So we saw that almost rankings grew by three ranks. We saw it go from about 10 to 7. That rank improvement was solely based on human analysts contributing what they knew about threat actor relevance. So one of the coolest parts of my research, I think, is that it's even more powerful than just the attribution decision itself. The technology demonstrates potential to use ML-powered attribution engines as a predictive monitor. So if you, for example, the analyst puts in some observables from the attack, the machine calculates, okay, these are the threat actors that might be behind the attack, and if it was Unit 1884, which these are all Stanford-themed threat actors, but if it was a spooky tree or Unit 1884, these are the different TTPs that you would see next. And then the analyst goes back in and says, hey, here are more observables of what I actually saw in my network. Here are the IPs, the hashes, the specific forensic details. And then the model goes in and says, okay, here are updated attribution results. Here are different TTPs that could come next. So it's actually, the attribution model is actually a bridge into this world of potentially being able to predict the next move of a threat actor. What is their next TTP and how can we catch them before they do that? So, as I mentioned, what excites me most about the application is this application for threat hunters to have a predictive sense of what TTPs might be coming in the chain, given a limited visibility into the kill chain itself. Additionally, these approaches help balance automation with interpretability. I talked about how powerful it is to go from those binary yes or no statements within the MITRE website, and you'll see it if you go onto MITRE today, is if you go onto any group's page, it just lists a list of 10 to 15 TTPs associated with the group. But instead of just those lists, imagine if we had sort of relative rankings of where those TTPs fall. Which ones are more useful for attribution? Which ones are less useful? What is their MO, right? Really understanding the threat actor. And also, it was clear that human in the loop, more contextual information increases performance a lot. So I can only imagine how much better the model will perform if we include details like victimology, like you saw the LLM performing better when it saw more information about the malware. Things like that could actually be really relevant inputs for a machine learning model. So in many ways, the model felt like a decision support tool for me, a junior analyst potentially to offer a varied perspective from a senior analyst and give them TTPs that maybe they hadn't thought about before and weren't originally considering. So there's potential here to help civil society groups who don't have tooling for attribution, arm governments with potentially more proactive intelligence about their decisions and policy-relevant national security decisions, and even equip private sector organizations with more intelligence about what's to come next. So in the end, I think it's not just about having access to more data in machine learning. It's about being able to gain actionable intelligence from that data to make decisions. So I think that's sort of what this end-to-end pipeline represents for the future of ML and threat intelligence. So with that, thank you so much for listening. I'm super happy to take questions now, and yeah, I'll be around at the conference this week too. Thank you.
Thank you so much. We have a couple questions on Slack. Are there any in the room?
I know this is really cool work, but just a question as far as the human in the loop component. One of the big concerns with attribution is always false flag operations. And with the human in the loop, it seems like this might be more susceptible to that kind of prompting, especially with junior analysts. Have you thought about whether that's something that needs to be baked into the model?
Yeah, so the human in the loop, the way that we used it in the research was just to add additional context into which threat actors are relevant at any given time. For example, we had, I think one of the threat actors in our set was like Muddy Water, and they haven't been active since like the early 2000s. So having a threat analyst go in and input that, hey, these threat actors are actually like super active right now, and these other threat actors are not that active, that's what really like pushed it over the edge in terms of helping with those make slightly more informed decisions. But I do think there is a risk there of like the human then maybe not knowing as much or something like that. But I think there's a lot of room for understanding like where exactly does the human fit into the loop. But I do think that any contextual information about the attack is helpful. And obviously it's built to be like not an ultimate autonomous decision. It's definitely built to work with the analyst, because otherwise like a decision like attribution is very, very high stakes, as you mentioned.
This is great, thanks. Can you talk more about the criteria that you used to select the threat intel? And just thinking out loud, like I would imagine that like a CTI analyst or a threat hunter might have different definitions of what's considered good threat intel, right? Like, does it have observables in it, forensic artifacts? Otherwise, I don't care, and that might affect the outcome. So,
yeah. So for my research, the primary selection criteria was, is it on MITRE, and are there human TTPs that have been identified from it that I could then use as comparison? So I looked at, it was all open source intelligence, and then all of the PDFs were basically, they did have observables in them, and they were also cited on the MITRE groups page. So yeah, it's true. Like there's so many types of intelligence, unstructured. That's like one of the biggest challenges in cyber. The criteria for me was pretty simple, that it was on MITRE and that it had attributable TTPs that like analysts had extracted from that report. So I kind of used that as like, oh, humans have vetted this before and read it and found something useful from it.
You have lots of questions and praise also in the Slack. The first question I want to read is from Dave Wilburn. He says, I'm kind of curious how this compares and contrasts to Matt Behringer's ATP and Tinder going atomic work. a few years ago prior to LLMs. My thinking would be that the pro with your work here is you wouldn't need a highly structured database and can just shovel a bunch of prose reports into the system instead.
Yeah, that's interesting. I'm actually not familiar with that previous work, but I would love to read it.
He's on the Slack too. You could,
Okay, awesome. Yeah, but I think that is true that the power here that I saw, and I think there's a lot of room for additional future work, is that, yeah, you're able to just throw at it like a PDF that's unstructured. And as I said, that's super common in threat intelligence, that a lot of these reports just end up sitting on a shelf and nobody reads them. And obviously it's relevant in the moment, but then months after, it's not as relevant anymore. But this is a way that we can actually transform some of those reports into, useful intelligence about a threat actor.
great. Okay, this next one I think is similar from Jake Nicastro. He said, if you were given the raw forensic data from an incident response rather than just a public report, how would you adjust or add to your approach? And is this something you've been able to experiment with?
Yeah, so I'm currently experimenting with this. What would happen if you throw it observables that maybe aren't in written language form? So that's where newer approaches like hide are pretty cool, because you can still use an LLM in the loop to construct something out of that observable, like make it into a sentence that would be found in a threat intelligence report, or build a paragraph around it that really demonstrates that behavior of the threat actor. So that's sort of what I'm exploring right now with the approach I talked about called hide. And yeah, I'm excited to see where it fits into this. I think there's definitely potential to still use embeddings to derive TTP information.
Okay, I'm gonna ask one more from the Slack. This one is, attack is designed to give categories to attack components based on their micro goal, why to do it, way of seeking the goal, what, and specific information towards that effort, how. What if attack is wrong? Would the LLM have better results if it were not bound by this taxonomy and instead allowed to structure its own?
Yeah, I've thought about this a lot. Like, how do you actually eval an LLM on something where you don't know if the human results are the best? So I think that's a growing discussion in the eval community, how to build evals that are actually precise and accurate. But I think it could be that, like the research showed, that it's still useful, even though it showed on paper raw comparisons to human TTPs were fairly low. It still, was useful in terms of training a model to do a task. So I think that in and of itself shows that there could be something outside of MITRE. And obviously there's limitations to MITRE itself. People say that MITRE is just the starting base, and then you build TTPs off of that to be more specific and precise. So I think there's potential for that. The only thing is CTI itself has so many different people do so many different things that it's so hard to standardize already, that attack really still represents a standardized way that different threat intelligence teams can report about attacks and incidents.
Awesome. I do think we have time for one last question. Oh, go ahead.
Thanks for the talk. It was great. I have a question related to uncertainty. So say I have like a net new report come in, right? And it's about some new threat actor group that hasn't been previously observed. Is the model able to abstain from making a guess in that case? And is there a way to quantify like how certain we are that this is the threat actor?
Yeah, that's a great question. So that's something that I'm working on right now. Can you include something that's unknown? Or can there be a threshold for when the confidence levels are so low that it just defers to unknown? Right now, it ranks threat actors still, but it ranks them pretty low, like with low certainty, like the percentage or the probabilities that you saw on the right side of the screen when I showed. But I think there is a way that like human analysts could inform that sort of threshold of like, oh, this is so low that like we wouldn't even think about this or care about it. It might be a new group or these techniques we've never seen before. So yeah, I definitely think that would be a cool addition to this.
Awesome. Thank you. Thank you so much. It's a great talk.